Oh, is there any like?
Sorry.
No, I do. Oh, but my pocket has 14 boxes.
Oh,
No, it's good.
I need to get birthday
I
presents.
don't know how do you want
I don't want to get any toys. I want toys.
Okay, everyone. We had a bunch of trouble with technology last week, but it seems like screen sharing is finally working for us. So for those of you at home, hopefully this actually works for you. We didn't finish what we were going to do last week, so I'm going to start by going into the course materials session 2 folder, and we're going to finish going through the PowerPoint just on how to use the graphing features in SPSS. And then after we do that, we'll go in and do an Excel exercise for today. So we'll do some SPSS as the first part of the lab, just finishing up what we didn't get to go through last week, and then after that we'll be working just in Excel for today. So everyone should open up the same data set that you had open from last week. If you saved a newer copy based off of what we did in it last week, then you can open that. Otherwise, open the version that's on Blackboard under Course Materials, Lab Section 3 and 4, the Community Health Survey 2011 data.
The editing graphs or the graphing and descriptive statistics.
So descriptive statistics is the PowerPoint, but you should be looking at the, you should also be downloading the SPSS data set, which is not in a specific weeks folder. It's in the general class materials folder.
Yeah.
So it's right here, course materials, sections 3 and 4,
Okay.
CHS data set, and then you just want to download the one that's red, which is the actual data set, because that's what you'll be using to do some of the graphs today. Okay, this is actually showing them what we're doing. Okay, so we're going to skip past what we did last week. If you recall, we went through SPSS descriptive statistics. We did frequencies, descriptives, and then we did a little bit of crosstabs. And so we did with the crosstabs last week, and then it also gave us the clustered bar charts, if you recall. And so just right here is the crosstabs menu that we ended with last week, where we put insured and race ethnicity. We asked for a chi-square, and then this is essentially what we got out, except that we had flipped it last week, where race ethnicity was the rows and whether or not they were insured was the columns. And then we also got a clustered bar chart. So today I'm just gonna show you quickly how to get some of those graphs also out of the graphing dialog. You don't necessarily have to do an analysis to get some of those graphs. So last week we got a histogram, a pie chart, a bar chart, and a clustered bar chart, each from doing different types of analyses or asking for different types of statistics. You can also just get those charts by themselves. So if you go into your graphs menu, so last week the first thing we looked at was the transform menu, and we did a compute command to compute a new variable. And then last week we spent most of our time under the analyze menu looking at the descriptive statistics. Today we're going to open up the graphs menu, which is next to analyze, and go down to the third bottom option, which is legacy dialogues. And then in that submenu, go to the 3D bar menu. And I see that we have already a difference between the two versions of SPSS. So let me just open up my SPSS data set real quick. So I need to do this together. So this PowerPoint will be a little out of date for what we're doing because they have updated this menu a little bit. This is what we used to get, but I see it from what other people have opened that they're getting some other things. Give my computer a second. Legacy dialogues. So you can see here that this now has 5 options, which in the version that I taught with last year, which was 19, it only had 3. So in the past year, they've really upped that. I think I said we're doing 3D bar. Oh no, we're just doing simple bar charts, sorry. So do legacy dialogues and then just do bar. And that'll get us the menu that we have in the PowerPoint. And so you should have what you see here, which is simple, clustered, and bar, or stacked. So the simple bar charts are what we did last week when we ran a frequency where we just looked at the number of people that were in a bunch of different categories. The clustered bar chart is where you're looking at 2 different variables combined, and so that's what we did where we looked at race ethnicity versus insured and uninsured. And so the first one we got out of the frequencies command, and then the clustered bar charts we got out of the crosstabs command. You can do both of those things by just going into the graphing menu as well. So if you go into, you just keep it on simple, that's the default, and you do summaries for groups of cases, that's also the default, and then you do define. And so today let's do race ethnicity. We'll look at, again, how many people we have. Excuse me. So we do race ethnicity in the category axis, and we can just keep it as the bars represent the number of cases. So as you can see at the top, the bars can represent some different things. So if we wanted race ethnicity to be our category axis, but we wanted to look at their average mood, remember we created that mood item that was basically a measure of depression, we could put that measure of depression in here and ask for another statistic and ask for the mean, for example. But for today, we're just going to do the number of cases, and then, as always, we're going to do paste, and then you'll see the syntax for that. It's very simple, and then you can just select that and run it, and you should get pretty much exactly what you got when we ran the frequencies last week.
Sorry.
Yep. Which part did you need?
The pasting.
Oh, so that is just under graphs. Define, paste is always just right next to OK.
No, but right. When you're copying and pasting into what? I'm sorry.
Oh, so I just pressed paste and it went right into my syntax window?
Yep.
and then I just selected that and ran it. So you wouldn't have two, you'd only have one. So you just select that phrase and run it, and then that gives you the exact same thing that you got from the frequencies. So if you want the chart by itself, this is a way to get it, although in general it's going to be much more useful to get it combined with the frequencies analysis, because that will also give you ends and percentages for each of the categories. Did you not get it?
I did something wrong, I think.
It's your syntax window is probably just not. It's probably
Well, I
hiding
had
down
data
here.
set up top. I didn't
Here,
copy the graph.
It's just hiding down here.
So, okay. So I'm copying this part of the data set activated.
You don't have to copy it. You just have to highlight it and press that green button.
Okay, never mind.
Yeah. Oh, no, it doesn't matter whether you select the data set part or not. Just, yeah,
All of
highlight
it?
that. Yep.
Okay.
And then I just want to show everyone also, quickly, I'm going to open up Microsoft Word. Of course, on this computer, it'll take 10 minutes. Because for some of your assignments, you'll need to show output. And so I just want to show you quickly that you can very easily right-click on that output and just do copy, or you could do copy special. Copy should work. You do copy, and then you just can paste it right into Word. Where's paste? Paste. And that didn't work, of course.
There's the arrows. Oh, when you do paste.
Oh, there we go. It's up there, hiding up there. So it's pretty straightforward. It's just the way you copy and paste anything else. But I just wanted to show everyone that. The one thing that I will note is that non-graphical output, so for example tables like the frequencies table or the crosstabs table, will paste a little bit differently. By default, Word will paste those as text. So let me just show you quickly the two different ways that you can do it. So I'm just going to do frequencies of race ethnicity. And remember, this is also where we had gotten that original bar chart to begin with. If I just do frequencies of that and I copy that, it's going to paste in as a text table. So you probably can't tell, but this is actually a table in Microsoft Word. It's not a picture. So this is a picture. You can't do anything with it. This is a table. Normally, having a table is probably good. However, sometimes Word will mess up the way that these tables look when you try to paste them in there. So you have another option. If you just do paste and then do paste special in Word. So I don't know, how many of you know about paste special? Okay, so anytime you're pasting, you have a lot of different options for how you want the object to be pasted. By default, Word chooses one for you, but if you do paste special, which can everyone see where I'm going right there? I just have clicked on paste with the down arrow below it, and then paste special is this option right here. You have a few different options for how to paste it. In this case, it's only giving us text options, but if I were to go back and I were to right-click on this table and do copy special, I can also ask it to copy it as an image, and then hit OK. And then when I go back here, I can also ask it to paste it as an image. So if I want it to be a picture, and I don't want it to get screwed up in any way by Word, and I want it to look exactly the same as it looks in SPSS, that's an easy way of turning it into a picture. So now what you have is a picture of that table instead of a text version of that table. You can't edit the picture, obviously. You could edit the table, and so it's, it depends on what you're trying to do, whether one is more appropriate than the other. So I just wanted to show everyone that really quickly. Okay, so that is how to get the simple bar chart. And then let me show you how to get the, so we want to compare the different racial and ethnic groups on their levels of depression, like I was saying before on that mood variable. So we could do bar again. And we're going to keep these options the same, and we're going to do define again. And now here we're going to add So if you don't have this average mood variable, you should, because I downloaded this from the Blackboard, so it should be in there for everyone. If you don't have it, then just follow along on the screen. But I'm just going to select that average mood variable, which is that depression item that we created out of the 6 different questions. It's the second to last variable. Remember that if you go on that list and start typing average mood, it'll bring you right there. But it's also the second to last variable, so it's very easy to find. We're going to go to other statistic up here in bars represent. We're going to move that variable in here now. And by default, SPSS is going to assume that what we want is the mean of that variable, which we do in this case. But you can also choose a bunch of other things. So you could do the median, you could do the mode. The sum is rarely going to be helpful. But there are a bunch of different things you can get out of this. In most cases, what you want will be the median, or I'm sorry, the mean. And so I'm just going to keep it like that. And I'm going to paste it. And then remember that the way this version of Windows works, it hides all of your data sets under the SPSS icon. So when you need your syntax, you have to go back and find it. And then we just have, you notice that it didn't do much. Instead of saying what we want is the count of people by new race, it's now saying what we want is the mean of the mood average item by new race. And so if you run that, instead of getting what we got before, which was how many people are in each racial ethnic group, what we're getting is how depressed in general people are in each racial ethnic group. And what you can see is that on average, it seems like the Hispanic people are slightly lower on this index of depression, and the Asian Pacific Islander non-Hispanic individuals are marginally higher than everyone else on this. And as we go through the course, we'll talk about ways of figuring out whether these differences are meaningful or whether this is really nothing. Because as you can see, these are probably like 4.15, this is probably like 4.1, this is probably like 4.2. So we don't know how meaningful those differences are or not. That's what we'll talk about later in the course. All right, so we have those two charts. The next thing we want to do is the legacy dialogues box plot. And a box plot is going to show us what the scatter around the mean is. So it's somewhat similar to a histogram, which we did last week, but it gives you slightly different information. It's going to display graphically the interquartile range and the skew around that. So we're going to go to graphs, legacy dialogues again, and we are going to go down to box plot. I think we can just probably do simple box plots. Okay. Let's just do simple box plots, summary for groups of cases, so this is all good. In the PowerPoint, I had chosen a different variable, but for today, let's keep it the same, and let's do their mood, which is the very last, second to last variable again. We're going to do that as the variable. So that's the continuous variable that you want to know more information about its spread and its distribution. And then categorically, we're going to do race ethnicity again. So we'll look at whether some groups have a wider variation across their means. So we saw that their means weren't terribly different. There was a group that was slightly lower than everyone else and a group that was slightly higher, but in general, they didn't seem to be that different. This will tell us whether or not there are different distributions, not just means. So it tells you more information than just the bar plot. Okay, so I'm back in my syntax now, and I'm going to highlight the examine syntax that we just got and run that. Don't forget, like I said, sometimes it'll give you this case processing summary. It's always good to look at because it'll tell you if you're missing anybody on the analyses. So if we saw, for example, that one of these racial ethnic groups was missing a bunch of people for some reason, we want to look at that because maybe it's a question that didn't apply to a certain group or something like that. And then we go down here. Can anyone tell me what this middle bar inside the box represents?
Median.
Sorry? The median, right. So that's the 50th percentile, that's the median. And then the two bars that cap off the actual box, what are those?
the ranges.
They're the interquartile ranges. So this is the 25th. So it's easier to see it on this one. This is the 25th percentile. This is the 75th percentile. So the box is the interquartile range. The top whisker, as it's sometimes called, these are sometimes called box and whisker plots. The top whisker is the minimum, and the bottom whisker is the maximum. Or, well, actually, in this case, this is the maximum, and this is the minimum. It depends the way that.
How is it 25%?
So, well, in this case, this is 25, 50, 75, and then this is 100%. All 5 of these groups are actually. So in this case, one of the groups doesn't have any outliers. So it's the whiskers are supposed to correspond to the minimum and the maximum, but if the variables have any strong outliers, it's going to exclude them from the whiskers. So as you can see, in this case, we have a bunch of people who are outliers, and what it's giving you is their ID numbers, so you can try to identify them. So there's only one group that doesn't have any outliers, but as you can see, they all have a strong skew towards the lower end of the depression spectrum.
How do you know that's 75 and not like 80 or 85?
In terms of, well, that's how it's defined.
Okay.
The box is defined as the interquartile range.
Oh, right.
And so the outsides of the box are always the 25th and 75th, and the middle, the line through the middle is always the median or the 50th percentile. You know, as we talked about last week, it's rarely exactly 75th because oftentimes what you'll get is like up to 72% fall here, and then above that is like the other 20. Like it often can't perfectly split it into 75, but that is basically the rounded 75th percentile. So the closest thing to the 75th percentile you can get within whatever variable you're looking at.
So I mean, I'm not very good. Actually, I suck at reading now box plots. So what is this telling you right now? You have the median.
So you can see this group's median.
This is depression, right?
Yep.
So.
And this, I think, it was the Asian Pacific Islander, non-Hispanic group again. So their median, just like their mean, is a little bit higher than everybody else's. The Hispanic group's median is a little bit lower than most other people, except this other group here. They all have the same maximum, so all 5 of the groups have at least one person that goes to 5. You can see here that the Hispanic individuals and I believe this is the other group, both have lower minimums, whether you include outliers or not. So the other group doesn't even have anybody that goes below whatever this is, 1.2 or something like that. The Latino group does have some outliers there, but their trimmed minimum is lower than everybody else's. And you can see the minimum here is higher, minimum here is higher, minimum here is higher. So it just gives you a sense of what the spread is like. But definitely we have some outliers in all of these groups in terms of this variable.
So how do you find the mean with the box plots?
So the box plots don't have the mean. We would go back up to the bar plots to get the mean. So these are the means for each of these groups. And as you know, the means are affected by skew. And so that's why it's also good to look here, because all of these variables have a lot of skew in them. And so it's good to know that those means are being pulled towards the lower direction by the skew in these variables. All right. And then the last thing we'll do is look at a scatter plot. So we will do graphs, legacy dialogues, scatter dot. It's the second to last one. So this one is helpful because it's not as easy to get by just performing a descriptive analysis. So pretty much everything we've looked at so far except the box plots you can get by just doing like frequencies or something like that, including this histogram, which I'm not going to show you because it's very similar to the bar chart. But the scatter dot is good to look at if what you're looking at is 2 quantitative variables and their association with each other. So we're going to define here. And I think what we should do is look at age, which is Q8.1. Something. It's demog1. It's this second quantitative variable right here. We'll put that on the x-axis. So just like last week when I said that it's good to, if you have an exposure outcome hypothesis about something, it's good to put the exposure as the rows and the outcome as the columns when you're doing a crosstabs. It's good to put the exposure as the x-axis and the outcome as the y-axis if you're doing something using a plot. So we'll put age as the x-axis because, again, age is something that you can't change. So most demographic variables are not considered the outcomes of anything. They're considered to be the exposure. So we'll put age there, and then we'll scroll to the bottom, and we'll get average mood, and we'll put that on the y-axis. And then once we have that, we'll just paste that back into our syntax and scroll over to our syntax. And we'll just run that last plot. And you can see here that in this case, it's not a super interesting plot because of the way that the depression items are so skewed. We're seeing a ton of people all the way up here, and so it's not really easy to differentiate what's going on in this image. So this would be a problem. We would want to consider maybe some ways of transforming one or both of these variables to look at them in a better way. But just to get a rough and dirty estimate of what's going on in this image so that it's not as clouded by all these different dots, we can double-click on the plot, like I said last week, or open up our graph editor. And right up here, we have a little line that's in between a bunch of dots. It's a button above it. And if you hover over it, it'll give you a little dialog box that says add fit line at total. So we want to click on that. And if your computer does not do linear by default, then select linear and do apply, but most of them should do linear by default. And that'll give us an image of what the general association is between these two variables. And so as you can see, it's not super steep, but it is slightly positive. So they are slightly positively associated, which would mean, can anyone tell me what?
Age and depression. There's a relationship towards it.
In what way?
Higher the age, higher the chance of depression.
Exactly. So older people seem to respond with slightly more depression on these questions than younger people. But again, we'll talk more as class goes on about ways of assessing whether this is really a meaningful association or not. And of course, there's no syntax for that, so changes in the graph editor don't produce syntax. But they do save here in your graph when you close it. So if you want to keep those, you can just, as I showed you, copy and paste those into Microsoft Word. You can also save those plots as special files, but they can only open in SPSS, and so it's not all that useful. If you're done making the plot, then you might as well just copy and paste it into Word.
If you want to get rid of it.
If you want to get rid of it, you can actually just delete it. So once this opens, you can click on it in the image, you can click on the actual line, and right-click, and it should have a delete option, if it ever opens. You wouldn't have been able to get that box to open.
Delete? No.
Seems to freeze. If you if you hit delete, that'll do the same thing. So that's another way of doing it. It's just to click on it and hit delete. All right. The plots that I'm going to show you for today in SPSS. I do just want to remind you again quickly how to do. Well, actually, let me just quickly show you what that will look like. So this plot is a plot of two quantitative variables associations. A bivariate Pearson's correlation is how to look at that numerically. And so we would just do analyze, correlate, bivariate. And that'll get us to our correlation menu. And then in this case, you don't pick an x and a y variable. It doesn't matter which is which. You just put both of them in there. So we'll just get that age variable, and we'll put it in there. And we'll get our mood variable, and we'll put it in there. And then all of the default options are good to go, and so we'll just paste that into our syntax and run that.
Sorry.
Yep. So analyze, correlate bivariate.
Mhm.
And then you're just going to put your mood and your age items in the box, and then that's all you need to do, and then you just paste it. And then we'll run that. And as I said, like, we have to interpret this with caution because there is so much skew in the mood variable. But you can see here that, as we saw in the plot, there is a positive association, and because of how many people we have in this data set, it also seems as though that positive association is statistically significant. However, correlations range from 0 to 1. They're a scaled statistic, and the closer they are to 1, the stronger they are. So given how close this statistic is to 0, we can tell that it's a really relatively weak correlation. So as we'll be talking about throughout the semester, there's a difference between like a meaningful association and a statistically significant association. Sometimes you can have a very meaningful association and you don't necessarily have the power for it to be statistically significant, and vice versa. Sometimes if you have enough people, even a really weak association can be statistically significant. Okay, and so I just want to remind everyone one last time, because the next few weeks we'll be talking about probability, and the way that we'll look at that is oftentimes through a crosstab. I just want to show everyone again quickly that to do crosstabs, we do descriptive statistics, crosstabs. In this case, let's do race ethnicity as the rows. I want to pick a variable that has everybody on it. So we'll look at whether they are Hispanic or Latino. Oh, actually, no, because that's actually combined with the other variable. So let's do insured, uninsured again, because that's an easy one that everybody has. And in this case, I'm not going to ask for the chi-square statistic. We'll do that later in the semester. I'm just going to ask for the row and column percentages.
Wait, say that again?
So that's under cells.
Analyze.
Analyze descriptives, crosstabs, and then under cells, we're going to just click row and column. And that'll give us percentages for the row and percentages for the column, which, as you talked about today, are both forms of conditional probabilities, which is what we'll be working on in Excel today. Sorry to be rushing, but I want to make sure that we get to the actual Excel piece, because that's actually more important. I mean, this piece is important, but we're going to be doing this manually in Excel in just a second. So we are going to paste that after we have it set up. So rows is race ethnicity, columns is insured, uninsured. Then we're going to paste that, go to our syntax, and we're going to run that. And then, again, like we saw last week, and so when SPSS says percent within race ethnicity, that means insurance conditioned upon race ethnicity. So among white non-Hispanic people, 95% are insured, 5% are not insured. Among insured people, 47% are white non-Hispanic. Among uninsured people, 19.8% are white non-Hispanic. So it's a little bit, it takes a very long time to get used to reading that. So I always ask for both. And then depending on what you're trying to do, you can figure out which one you actually need to use. Because you typically won't report both. You'll choose one or the other. You'll say, among people of this race, this percent were insured, or among the insured, this percent were this race. You'll typically do that consistently throughout. But I just want to show you that, you know, each of those has similar information, but it can lead to a slightly different way of looking at it. Okay, so for those of you who want to, go ahead and save your syntax, save your output if you'd like to, save any changes you may have made to the data set, although we didn't modify any variables today, and then go ahead and close all of that. And then there's a Excel exercise posted on Blackboard now for this week's lab. So earlier we were finishing up stuff from lab 2. Today we're going to move on to the lab 3 folder. And so remember, we're lab sections 3 and 4. And then you can just do lab 3 probability exercises. Let me know if anyone has trouble opening that. By the way, did everyone get SPSS to open today? Yeah. Nobody had any trouble with that? Okay, good. Once you have Excel opened, anytime you download a file from the internet, Excel is going to try to stop you from editing it because it thinks that it could be malicious. So you always have to do this enable editing thing. Otherwise, it's not going to let you do anything with the document. All right, so today in your lecture, you talked about conditional probabilities. And probabilities can be are oftentimes used in one of two ways. And so under the first tab in Excel, remember tabs are at the bottom, and you can have different stuff in each tab. So under probability 1, I have probabilities of the event or the exposure being receiving a vaccine versus receiving a control, and the outcome being whether or not someone got a certain disease. So that's the first way that we oftentimes look at these 2x2 probabilities. And then another way that's very common in public health is under probability 2, I have whether or not someone has a given disease and whether or not a screening test actually identified that disease. So these are two different ways. In one, the disease is the outcome and some sort of event or exposure is the exposure. And then in this case, whether or not they had the disease is often put on the left-hand column as the exposure, and then we look at how well the test performed for people who did and did not have the disease. So for example, this could be some sort of new HIV test where people either have HIV or they don't, and we look at whether this new test actually detected it, both for people who have it and for people that don't, because what we want is a test that is going to be really accurate at finding the people who do have it and not thinking that people who don't have it do, and vice versa. So we don't want to incorrectly say that people have it when they don't, because that causes false panic. And we also don't want to incorrectly say people don't have it when they do, because then they don't get referred for treatment. So those are two different ways that we're going to use probabilities. Up at the top of these spreadsheets, I have a couple of different definitions and rules for you. On Blackboard, there are also 2 PDFs that have these basic concepts as well, but you know, like I said before, they each say them slightly different. They put them in slightly different ways, so they're there for you guys to reference in case one of them is more helpful than something we're doing here or what you did in lecture. And I also posted a link to the Khan Academy probability series. They have a bunch of different videos. In total, I would say that their entire probability series that I posted would take you like 2 hours to watch. You probably don't need to watch all of them, but some of them, these concepts can be really difficult to struggle with because people don't think in probability very well. And so feel free to go on and watch at least some of those. He may explain them in a way that you haven't heard before and that really resonates with you. And that Khan Academy website also, in addition to having those videos, also has exercises that you can do. So if you want to, test yourself to see whether you're getting this or not, there are also exercises that you can perform on that website. And it's free to join. I believe you do need to sign up, but other than that, you can have your spam go to your Hunter email account. Okay, so what I want to do today is go through how to calculate some of these probabilities. So for each one, I'm going to show everyone how to do the first one, and then I'm going to ask you guys to work by yourselves or work together with other people to try to do the other 3 for each set. And then, of course, we'll do them together, and the answer sheet will be posted online afterwards. All right, so the probability that someone got anything is just the probability that they are in that group, or it's just the number of people in that group divided by the total number of people. So for the probability that someone got the vaccine, can anyone tell me the first cell that I need to select when I'm making my function? So remember, we're going to make a function by doing equals and then we're going to select a cell, and then we're going to divide that cell by another cell in order to get a proportion. So which is the cell that I need to select first?
C8, C9. C9.
So it's not C9 because that is people who got the vaccine and got the disease. So it's actually all the way over here, it's E9. So that's the total number of people who got the vaccine. Oops. It's E9, and then what am I dividing that by?
E11.
E11, perfect. Okay, so everyone take take like 2 minutes to try to figure out the other 3, and then when everyone's done, I'll post them. I'll just type them in here. Raise your hand if you have any questions or problems, and I'll come around. And remember, try to use formulas for this, because the thing is, if all of a sudden I had realized, like, oh my god, I ran the crosstabs wrong and these numbers are totally different. If you have all these formulas in here instead of doing the math by hand, if I told you to type in all new numbers here, all of these formulas would update with those new data. So if we realized, oh my god, we ran everything wrong, we need to do it all over, we actually wouldn't have that much to do over. We could just re-enter the actual numbers, and all those formulas would update with the new numbers. Okay, did everyone get what I have on the board here? Raise your hand if you got any of these wrong, and then we can just talk about what maybe you did incorrectly. So everyone got 0.5 and 0.5 for the vaccine and the control. Does everyone understand what that means? That those were each 0.5? What does that mean?
Total vaccine over total?
It means that there was a 50-50 chance that you got either the vaccine or the control, which is what you would expect if we were doing a randomized trial. We would expect that half of the people would be randomly assigned to receive the vaccine, and half of the people would be randomly assigned to receive the control. These are called marginal probabilities. The marginal probabilities in the rows should add to 100%, and the marginal probabilities in the columns should add to 100%. So the probability of the vaccine and the probability of the control should add to 100%, which they do. That makes sense because you can only be one or the other. Same way here, the probability that you got the disease and the probability that you did not get the disease should add to 1 as well, because you either had to have gotten the disease or not gotten the disease. So you'll see that here, 0.24 and 0.76 also add to 1. And again, probability is on a 0 to 1 scale. You multiply that by 100 and you get percentage. Percentage and probability are the same thing. They're just scaled differently. Can someone just tell me what these two bottom probabilities mean? The probability you got the disease or did not get the disease? Thinking about what I just said about how you translate probabilities into percentages.
It's just the amount of people.
So what is the amount?
Well.
What percentage got the disease? 24%. Perfect. Okay. So now, before I said that this was not what you would use to get the probability that you got the vaccine, because that's the probability of getting the vaccine and the disease. Well, now that's exactly what we want to calculate here. So what we're going to do for probability of vaccine and got disease is take that cell and divide it by what? By the total. Yep. So we just take that one cell, we do equals, we select that cell, vaccine and disease, and we divide that by the total. So everyone quickly take some time and try to fill in the rest of those 3 rows. This total, yep. Yeah. So you can bold that if you want. That's called the grand total. These are called marginal totals, just like when we calculate their probabilities, they're called marginal probabilities. It's because they live in the margins here. The bottom and the sides are considered to be the margins of the table. So these are marginal totals, these are marginal totals, and then this is the grand total. The grand total is not the sum of these and these, it's the sum of these or these, which are identical.
So why are we dividing by the grand total and not by those other things?
Because that is a conditional probability, which is what we're going to calculate down here. So the probability of having the vaccine and getting the disease is exactly that. It's the probability of being in vaccine and disease out of the totals. So these 4 are going to add up to 1.
Okay.
So just like the every 2 of these added up to 1, all 4 of these are going to add up to 1. Did everyone get these numbers? 0.05, 0.45, 0.18, 0.32? So for this first one, it's going to be the group who. So here we see what we want. What group we want. The group is vaccine and disease. So we pick that group, and then we're just dividing it by the total. And then we're going to do that for all the groups. So the next one is going to be vaccine, no disease. So we pick this group, which is the vaccine, no disease group, and we divide it by the total. And like I said, just like when the marginal probabilities each add up to 1, these joint probabilities will total to 1 across all 4. Because we're taking one of the 4 cells and dividing it by the total. Once we take all 4 of those cells and divide them by the total, we have the total. So if we were to add all 4 of these together and divide them by the total, we would get 1 because it would be the total. So marginal probabilities, two of them together add to 1, and then these joint probabilities, all 4 of them together add to 1. Yeah.
Can you just, I get what you're saying, what in words that we need to do this to probability of vaccine is just divided by 2,000 people who were vaccinated?
So that is what we're going to do below. So we'll talk about that in just a second. For what we're doing here, can someone just tell me what this 0.45 means? The purple 0.45. What does that tell us? What is this proportion tell
45%
us?
of the population got the vaccine and had no disease.
45% of the total sample, total population got the vaccine and didn't get the disease. Whereas only 5% of the population got the vaccine and did get the disease. 18% of the population got the control and got the disease, and 32% of the population got the control and got no disease. So just eyeballing that, what do you think that's telling us?
You should get the vaccine.
So the vaccine, it looks like a lot fewer people who got the vaccine also got the disease when compared to the control. So 18% of the control people got the disease, only 5% of the vaccine people got the disease. So it seems like, so far, getting the vaccine is a good idea. All right. So now what we need is to create a table of these probabilities instead of a table of these numbers. So what we want here is just to transfer these probabilities down into this table. And like I said before, we could just type in those numbers. So we could type in 0.05 here. But that's not going to be super helpful if for some reason we end up having to change the original numbers because we realize we did something wrong. So here we're just going to do this. If we do equals and then just select that number, it's going to pull down whatever value is in that cell. So I didn't do a function here. I didn't divide it by anything. I didn't multiply it by anything. I didn't subtract it from anything. All I'm doing is saying take whatever value is in this cell and make this cell equal to that as well. That way, if for some reason we realize we did something wrong here and need to change it, it'll automatically update it here as well. Whereas if you have a table and you have a bunch of different numbers in there, you update one, and if the others don't update, you end up having to update a bunch of different things. And so if you just make this cell, any cell that you want equal to another cell, it's better to do it this way than to just type it. So that's going to be that one. This is going to be no disease and vaccine, so 0.45. This is going to be control and disease, so D20, which is 0.18. And this is going to be control and no disease, 0.32. And then, does everyone have those four numbers? We're all good here? Okay, and then remember our auto sum feature? So we're going to select these two and get their marginal probability by using the auto sum feature. Remember, on your computer it's bigger, so it'll probably actually say auto sum next to it. So select across these two cells and press that auto sum button, and it's going to put their marginal probability next to them, which we had already calculated up here. Select the ones below it and do the same exact thing. It's going to put their marginal probabilities next to them. Select these two, do the same thing. You know what? I actually don't know for sure. It might do it in all four if we do auto sum. No, sadly. Yeah, just did the bottom two, but I thought maybe it would do it all four ways. And again, those numbers should match what we already calculated above. And again, as always, they should add to 1. Everyone good with where we are right now? Okay, so now we are going to do the conditional probabilities. Does anyone remember what this means?
Got the disease given they were vaccinated? Got the disease given they were given
Exactly.
vaccine?
So this little line here means conditional on or given that. So this is the probability that you got the disease given that you were vaccinated. The given that part gives you what you need in your denominator. So you got the disease given that you were vaccinated. So that means you got the disease and you were vaccinated out of everyone who was vaccinated. So what do we need to put in that cell? So no, it's not going to. So we're going to be using this table now of the probabilities here.
So 0.24 is the total of the vaccine.
So this is going to be equal to the got the disease and vaccine out of everyone who got the vaccine, because that's our denominator. Does everyone understand why we got that? So again, these two things combined, getting the disease and having the vaccine, gives you your numerator. And then the part after the line, the conditional piece, gives you your denominator. So it's got the disease and got the vaccine out of everyone who got the vaccine, which we do by saying 0.05 divided by 0.50. Here we're working with probabilities now instead of the actual numbers. So got the disease given the vaccine means out of everyone who got the vaccine, what proportion also got the disease. So it's got the disease and the vaccine, which is this cell here, 0.05, divided by everyone who got a vaccine, which is this cell here, 0.50. And so just do the same thing for the other three. Okay, did everyone get what we have up here? So we're going to do the same thing here. The probability that you did not get the disease, given that you got the vaccine, is going to be the probability that you did not get the disease and got the vaccine, divided by the probability that you got the vaccine, which is this one. So remember that the part to the right is going to give you which margin you need. So anytime it says vaccine, we need everybody in this row. Anytime it says control, we need everybody in this row. So we need that marginal probability there. And then we're going to do the same thing for these. So got disease and control divided by got everyone. Oh, Jesus. And then no disease and control divided by everyone in the control. Okay, then the last thing we're going to do here is calculate the probability. We're going to calculate multiplied probabilities here. So the probability that you got to the disease multiplied by the probability that you got the vaccine.
Is that the union?
Yep, so this is the union. So the probability that you got the disease multiplied by the probability that you got the vaccine is what? So which cells are we going to use?
C24 and E24? Isn't it?
So this is going to be the probability that we got the disease, which is here, times the probability that we got the vaccine. 0.12.
Wait, what?
So again we're going back to using just marginal probabilities here. So it's everyone the probability of getting the disease out of everyone times the probability of getting the vaccine out of everyone. So pretty much it's going to be 0.24 times 0.5, 0.76 times 0.5, 0.24 times 0.5. So this next one is probability that they did not get the disease, 0.76, times the probability that they got the vaccine, 0.5. So in this case, because it's a 50-50 chance for one of the two variables, it's going to look identical, basically. So we're just going to go back and do 0.24 times 0.5 again, but we're going to get that 0.5 from a different row this time. So then these are our final probabilities. Now with all of these different probabilities that you have here, you have all of the information you need to evaluate whether the vaccine versus control is independent of disease or whether getting the disease shows evidence of dependence on vaccine status. I'm not going to go over right now what those rules are. You'll be able to easily find them in the lecture notes, I believe. There are two different rules that you can use to figure out whether events are independent. There should be two different types of probabilities that are equal to each other, and that will tell you whether or not the events are dependent. I'll let you guys look that up and decide on your own whether you think this is independent or dependent, but then the answer will be in the spreadsheet that I post online, so you can look once you have had some time to think about that. I want to quickly go over this next sheet where we're going to be calculating a bunch of probabilities that are exactly the same as what we just did, so I'm going to go quickly through those, and then I want to talk a little bit more about these conditional probabilities again at the bottom. So here we're doing probability of disease. Everyone should remember that by now. What am I going to put there? What two numbers am I going to be dividing? So this first one, probability of getting the disease. What two numbers?
Over the total sample.
So which numbers?
734 over 1788.
So this time disease has switched.
Disease, sorry.
Yeah. So because we're now looking at how well a test actually figures out whether or not someone has the disease has changed places.
So 698.
Exactly. So it's 698 divided by 1788. So we're going to pick those cells.
I couldn't see the 698.
No, that's okay. And then we would do the same thing all the way down. So probability of no disease is right here out of the total. Probability of being positive is this out of the total. And the probability of being negative is this out of the total. So someone tell me a little bit about what these numbers are saying to us.
We haven't missed anybody.
We don't know that yet. These are just telling us general proportions in the sample.
Oh.
So when you have these marginal probabilities, it helps to look at the first two and then to look at the second two. So look at the first two and tell me what we're seeing.
It equals 1.
But
So
what are we
much-
seeing
how much
in
of
the actual
population has
proportions?
the disease versus how much population? How much of the population doesn't have the disease?
And what are we seeing?
Whereas
39%.
Right, exactly. So 39% have the disease, 61% don't. So roughly 1/3 of the population has the disease. And then what are we seeing with regards to the test results?
41% are positive. 50%.
So that's
Exactly. So 41% of the sample tested positive, 59% of the sample tested negative. So already we know that this is not going to be a perfect test, because if this was a perfect test, we would expect these numbers to be identical. So if this test was identifying everyone exactly the same as their true disease status, then we would have 39% testing positive, 61% testing negative. So we already know that it's not going to be a perfect test. Now we have to see how imperfect it's going to be. So someone tell me what I'm going to do to get the probability of receiving the disease and testing positive. Mm-hmm.
I'm getting some.
It was still using formula. So. What are you getting? Can I see your form? Nope. So it's we're again using the marginal numbers. So it's everyone who got the disease. Yep. So in Excel, if you get the box wrong, you can actually click it and drag it. So what am I going to do to get the probability of disease and positive?
so you go to disease and positive box 597.
Exactly. So in these first ones, we're using the marginal numbers. And remember, the first pair adds to 1 and the second pair adds to 1. In the joint probabilities, we are using the actual cells, and all 4 of them are going to add to 1. So keep that in mind when you're looking at this. Every pair is going to add to 1, and you're going to be using the margins. For these, all 4 of them are going to add to 1, and you're going to use the actual counts of the cells. So here, for the first one, we're going to do the probability of people who are in the cell that has both the disease and positive result. So that's 597 by the row. Then we're going to do disease and negative. So that's 101 divided by the total sample. Then we're going to do no disease and positive divided by the total sample. And then we're going to do no disease and negative divided by the total sample. And if you want to just confirm that that worked out perfectly, you just select those and you can do an auto sum below them. As you can see, we got 1 for that, so we know that we did it correctly, because those joint probabilities should be adding up to 1. And then remember, we're going to put those probabilities now into this table. So the probability of being positive and getting the disease is this first one. The probability of being negative and getting the disease is the second one. The probability of being positive and not having the disease is this third one. And the probability of not having the disease and being negative is the fourth one. And then we are going to auto-sum those and auto-sum and auto-sum. Are we good? Okay. By the way, a little trick. If you didn't want to do all the work that we just did, you could actually take these 4 cells and copy them and paste them here. And it's actually going to pull in the formulas that we used to get them from the, because we did the exact same things here. Actually, did we?
Yeah, I think we
Did I have the same? Yeah, we did. We did the exact same type of calculation for each one of these. So it's actually going to, so the answers that you got should be the same as the answers that I got here. We could have, are they not?
No.
Oh, I probably reversed the order of the questions then. Well, if I hadn't reversed things, then they would match
The
because
password is the same.
it would calculate the formulas. Oh, so I probably switched these around in the ordering of things.
No, I got the same. I got the same.
Everyone has these numbers though, right? Because these are correct. 0.33 is the first one everyone got? Okay, so we're good. And then everyone has this table looking like this, 0.33, 0.06, 0.08, 0.53. Okay, cool. So then, someone tell me what is going to be the denominator for these 4. So these are our conditional probabilities. Probability that you have the disease given that you're positive on the test. Probability that you don't have the disease given you're negative on the test, etc. What's going to be the marginal cells that we use to calculate those for?
Total positive and total negative?
Total positive for the first 2. This one is the denominator, so the number you're dividing by. And total negative 0.59 is going to be the denominator for the second 2. And then obviously for this first one, you're going to do disease and positive divided by positive. So that's disease and positive divided by positive. For the second one, you're going to do no disease and positive divided by positive. And then for these ones down here, we're just looking at them in the opposite way. So we're switching the ordering of things. And so then in these ones, we're going to be picking the same cells. So this is still going to be the positive and disease cell. So you'll see that the cells that you use are the same, but the denominator is going to change. So the numerator will stay the same, but in this case, the denominator becomes the disease, and then for the second 2, the disease. Actually, I did disease, no disease, disease, no disease. So the denominator will change. All 4 of these statistics, when we're talking about a diagnostic test, this does not apply to the previous situation where we're talking about the proportion of people who were given a placebo versus a vaccine and did or did not get a disease. When we're looking at a diagnostic test to see how accurate it is in predicting actual disease state, all 4 of these things have terms. These 4 types of probabilities have their own specific psychometric terms. So take a look at the lecture, see if you can figure out what those terms are. They'll be in the answer sheet as well. And then, given those terms, see if you can provide any assessment of how well the tool is doing based on these 4 different commonly used statistics. Some of them will give you the rate of false negatives. Some of them will give you the rate of false positives, which are both really important things. False negatives tells us how many people were diagnosed as being negative even though they weren't. False positives are the opposite. How many people were diagnosed as being positive even though they weren't? We want to avoid both of those things, like I said before. We don't want to tell people they have some disease if they don't have it. That would be a false positive. And we don't want to tell someone they don't have the disease if they do have it. That would be a false negative. False negatives especially are bad because someone is then actually has a disease and is not being treated for it. So that's especially bad, but it's also not so great to tell people that they have something they don't. People don't really like that very much. So see if you can find that stuff in the lecture notes. If not, go ahead and look at the answer sheet, and you'll see what they're called. You can look those up on Google, or I'm sorry, on Wikipedia. Actually has a pretty good page that discusses these 4 terms. So once you see what they are, if you're struggling with them at all, go ahead and look them up on Wikipedia because their page actually is pretty good at discussing what they mean. And then give an overall assessment of the tool and how well you think it's doing, given the rate of false positives and the rate of false negatives, keeping in mind that we pretty much want those things to be as close to 0 as possible. And again, the answer for that, I also put like a little blurb in there about what I would say about how well the tool is doing. So see what you think and see what you come up with for that. It's not posted yet, but I'll post it tonight.
Okay, just
Yeah, I'll post it when I get home tonight.
I just want to make sure. Yeah.